My name is Margot Lopez, and this is Learning Some Science Tonight. Today's topic is the Vera C. Rubin Observatory. This new, state-of-the-art facility is located in the foothills of the Andes Mountains in Chile, with some observatory friends to keep it from getting lonely. Reports are in that this observatory will revolutionize astronomy. That's a bold statement, so I decided to do some investigation, starting with the most basic question. Why do we even need another observatory? We've already got a bunch of them scattered around. The short answer is this observatory is different. For starters, the roof isn't painted pink. But more importantly, it's unique compared to other ground-based facilities because it can see more of the sky, move faster, and see fainter light. The mission of the Rubin Observatory is to build a well-understood system that provides a vast astronomical data set for unprecedented discovery of the deep and dynamic universe. The idea here is to collect as much clean data as humanly, or rather technologically possible. The key word is dynamic. The universe is constantly changing on millisecond timescales all the way up to billion-year timescales, and the Rubin Observatory will capture those changes by imaging every patch of the southern hemisphere sky in just 3 nights. And it will do that over and over for 10 years. 3 nights is crazy fast when you're looking predominantly at light from billions of years in the past. But a high image frequency is an important part of mapping and then studying how objects in the sky interact with each other. Or, more precisely, interacted with each other ages ago. The entire project was formerly known as the Large Synoptic Survey Telescope before it was renamed. Because conserving acronyms is useful, the process of gathering all these images is now known as the Legacy Survey of Space and Time, beating out the La Sirena Super Telescope, and my personal favorite. Over the course of the 10-year survey, the Rubin Observatory will visit each part of the southern sky more than 800 times. With all that data, more so than static images, we're actually making a fully dynamic movie of the universe, better than any other space movie before. Sorry, Star Wars, you had a good run. So, how do we go about actually collecting the mountain of data necessary to make a movie better than the second highest grossing film franchise worldwide? There are 3 major factors. A wide field of view, so you can see a ton of sky at once. A fast telescope, to move rapidly from pointing at one patch of sky to another. And a short readout time, to quickly save the image data. Let's start with the wide field of view. A telescope's field of view is based predominantly on the size and configuration of its mirrors. The Rubin Observatory's primary mirror is 8.4 meters in diameter, which is an objectively big mirror, but isn't all that revolutionary. After all, the Gemini observatories have been using 8-meter mirrors for 20 years. In fact, compared to other major telescopes, Rubin's primary mirror looks downright average. To be fair, many of these other large telescopes have segmented primary mirrors. Even so, I'm not sure how you compete with the aptly named Very Large Telescope or the Extremely Large Telescope. Good thing the Overwhelmingly Large Telescope was canceled. To be honest, I'm a little worried that the world of astronomy has dug itself into a hole. because where do you go from there? Ginormous telescope? The only problem I see is that it would have to compete with the Ford GT on acronyms. But I think in general, people's priority lists tend to have space ahead of cars. So they're probably fine. Circling back to the issue at hand, we've established that the primary mirror for the Rubin Observatory isn't all that big. So why didn't they just make a bigger one? Larger mirrors are harder to manufacture and more susceptible to deformation, so there is a physical limit on how big you can make a mirror. 8.4 meters isn't quite at the limit, but it's definitely pushing close. We also want a fast telescope, and whisking huge mirrors around gets much harder as they get larger. As it is, the mirror coating chamber barely fit through the tunnel on the way to the mountain. Yikes! So, while the primary mirror is important, Rubin's wide field of view actually stems from the combination of that mirror with two additional powered mirrors. The third mirror in the set is particularly important because it maintains the image quality across the wide field of view. Many telescopes don't have a third powered mirror because it makes the entire system more expensive, and more complicated to build because it's difficult to properly position all of the optics. Rubin's telescope solves that problem by casting and then grinding the primary and tertiary mirrors as one monolithic structure. Having a single piece of glass for the two differently shaped mirrors means that they are very precisely and permanently aligned, simplifying the alignment process of the overall optical system, which includes the camera lenses. The compact configuration also makes it easier to move the telescope around. With this fancy mirror design, the telescope's full field of view is 3.5 degrees across, or 9.6 degrees squared, an area big enough to see 40 full moons in one image. For comparison, a telescope like the one at the Gemini Observatory, with a similarly sized primary mirror, but no powered tertiary mirror, has a much smaller field of view, less than half a degree across. Rubin's extremely wide field of view is a huge advantage because we can collect a lot more light per image and cover more of the sky at one time. But that's not the whole story, because in order to actually make this a movie, we need to be able to move from pointing at one patch of the sky to the next quickly. That's where Rubin's telescope, officially known as the Simony Survey Telescope, really shines. The telescope, weighing a total of 350 metric tons once the mirrors and camera are installed, can rotate at the staggering speed of 10.5 degrees per second and tilt at a speed of 3.5 degrees per second, shown here in real time. It's essentially a 3-story house made completely of steel, and it can move from pointing at one part of the sky to an adjacent area 7 full moons away, and then settle and be ready to take the next image in a grand total of 5 seconds, which is less time than it takes me to explain how fast that is. Rubin's telescope is basically the Australian tiger beetle of the telescope kingdom. Now, I know what you're thinking. Their top speed is only 2.5 meters per second, about the same as a particularly competent toddler, which is to say, not particularly fast. But compared to their size, Australian tiger beetles are super speedy, covering 125 body lengths in a second. To match that, a cheetah would have to move at 200 meters per second, or 450 miles per hour. Furthermore, the Australian tiger beetle's compound eyes give it an extra wide field of view, making it the ideal comparison for Rubin's telescope. Now, that speed is only useful if the telescope's camera can start the next exposure immediately when you get there. To do that, Not only does the telescope need to settle quickly, the sensors need to have already downloaded the previous image data and be ready to take another one. We can compare different instruments by plotting number of pixels versus readout speed, or how fast they can save images in pixels per second. In general, better instruments will have more pixels and be able to read them out faster, so up and right is good. Some instruments are just small. It's not a super fair comparison because the Hubble is ancient in terms of sensor technology, but someone needs to anchor the chart. The Hypersuprime Cam in Hawaii and the Dark Energy Cam in Chile both have pretty good-sized focal planes, around 500 million pixels, but they're still pretty slow at downloading that data. The ZTF camera at the Palomar Observatory in California is a big step forward in readout speed, but it isn't significantly larger. The Pan-STARRS GPC-1 camera improves substantially in both metrics, with 1.4 billion pixels that can be read out really fast. Wait, where's the LSST camera? There it is. This camera can read out 1.6 billion pixels per second. That means the total readout time is a mere 2 seconds per image. That readout speed, combined with a fast telescope, translates to the median time per visit being just 39 seconds, allowing the telescope to do about 1,000 visits per night for 10 years. So that's the secret space movie formula. An extra wide field of view, an Australian tiger beetle for a telescope, and a readout time that's off the charts. You can't make a groundbreaking space movie unless you've got a state-of-the-art studio. And in this case, that studio is the observatory facility that supports the telescope. The telescope itself is mounted on a concrete pier directly on bedrock for stability, and it's enclosed by a 30-meter rotating dome. When the dome is open at night for observing, it has an additional screen to help keep out stray light, as well as provide an extra barrier on windy nights. The telescope and dome are connected to the service and operations building via an 80-ton platform lift that could lift 16 elephants and a half, but is more frequently used to transport the camera and the mirrors from the telescope down to the service building. The main service area contains a clean room for camera maintenance, as well as a large open space for mirror coating equipment. The control room is on the lower floor. And all the way at the bottom is the equipment needed to run the facility, like cooling systems and the pumps for the hydraulic oil system that helps the telescope turn so fast. The observatory's design is optimized to keep all of this heat-generating equipment, as well as the temperature-controlled office space, away from the telescope and dome. Nights on the mountain at 2,600 meters of elevation can be cold compared to daytime temperatures, and after warming up all day in the sun, the telescope needs to come down to this low ambient temperature at night as quickly as possible in order to avoid air currents inside the dome that would reduce image quality. That's also one reason the building is painted white and not pink or any other fun color. The white paint helps the building stay cool during the day, so it takes less time to adjust to the ambient temperature at night. Overall, it's an incredibly useful studio for creating our space movie. But wait, we still need a camera to actually record the movie. While most telescopes have several instruments that they rotate through, the Rubin Observatory is planning to use only one imager, the LSST camera. At 5.5 feet in diameter by 12 feet long, it is the largest digital camera ever constructed, about the size of a small car. But it starts to look tiny when compared to the ginormous telescope structure, so I thought it would be useful to appreciate the size of the camera in some more relatable units, such as corgi puppies. Assuming standard mailbox dimensions, this photo implies that each corgi takes up about 3/4 of a cubic foot, giving them some space to wiggle around and not be completely squished together. This is, after all, a humane operation. Given that the camera volume is 180 cubic feet, you could fit 240 corgi puppies inside. In addition to being giant, this camera has 3.2 billion pixels. That's about 250 times more pixels than a top-of-the-line iPhone, and those photos look crisp on billboards. To get that many pixels, we use a grid of sensors installed inside the camera in a cryostat. Each of those sensors, shown here in fuzzy pink, is 4,000 by 4,000 pixels. If we wanted to display the image from a single sensor on a regular screen, like a 60-inch 4K TV, it would actually take 2 televisions stacked on top of one another. That's perfectly doable in your living room and downright useful if you watch a lot of sports balls. Individual sensors are assembled into groups of 9 in a piece of hardware called a science raft, which also includes the electronics boards that are used to read out the sensors. Recall that for just one sensor, we needed 2 4K TVs. So to display the image from a science raft with 9 sensors, we'd need a total of 18 televisions. Still kind of fits? But we're not done yet. There are actually 21 science rafts in the camera. And we are definitely out of wall space. And court space. And these are 4K TVs, the newish fancy ones. What if instead we decide to go old school and just use a regular HD TV? In order to view a single image taken by the LSST camera, we'd need 1,500 HD TVs. Not to be confused with HGTV, which can be viewed on a single 4K TV. Each science raft is tested individually before getting installed in the cryostat, mounted in a grid pattern on a piece of hardware that has cleverly been called the grid. Each of these science rafts is worth over $1 million just in hardware, and they're installed really close together, which makes sense because you don't want huge gaps in your image between the sensors, but is also mildly terrifying during the installation process because it has to be so tightly controlled. These rafts are installed only 0.5 millimeter apart, meaning there's only a few hair widths of clearance on each side before sensors collide and crack. Turns out we have quite the knack for working within tight tolerances. Scaling up, it's like parking a row of $1 million Maserati sports cars just 1 inch apart. Unsurprisingly, people don't normally do that with sports cars, but they do with minivans. So that's the visual. We're parking $1 million sports cars 1 inch apart with nary a scratch. We do, however, have parking assist, namely a robot arm on top that reaches down through the grid and draws the science rafts up into their final position one by one. There are also some heavy-duty telecentric lenses down below, so we can closely monitor the entire process and abort if sensors are getting dangerously close. Raft installation is done inside a clean room to make sure that the sensors stay pristine, and so that there aren't any big particles or pieces of dust caught inside the cryostat that could later fall on a sensor and block a pixel. The whole process takes about 4 hours for a single raft, assuming it goes perfectly, which isn't always the case. Fully assembled, the focal plane is flat to plus or minus 11 microns, less than the width of a human hair. That's like taking an ice hockey rink and making it completely flat to within 1 millimeter, just 10 sheets of paper. But instead of getting to Zamboni the whole thing flat, you're stuck with 189 separate giant ice cubes to maneuver carefully into place. With all the rafts installed, the 3.2 billion pixel focal plane is 640 millimeters in diameter, or just a little over 2 feet. So that's a lot of pixels crammed into a small space, and a lot of space that can be crammed onto those small pixels. Speaking of space, these sensors can detect light of the 24th magnitude in a single image, and of the 27th magnitude stacked. That translates to seeing really dim light, really far away. For example, if you were to hit a golf ball all the way to the moon, LSST cam would be able to see it. Keep in mind that a golf ball is 80 million times smaller than the moon. I can't even see where they go at the driving range, let alone 380,000 kilometers away in space. This image was taken during the Sloan Digital Sky Survey, a project that, similar to LSST, wanted to map the sky and catalog as many objects as possible. This image is representative of how far into space the LSST camera will be able to see compared to that earlier survey. It will detect an incredible number of new stars and galaxies. In order to help sort out what it's actually seeing deep in space, the camera has 6 different filters for different wavelengths of light. It will be loaded with 5 of these filters at any given time, and it can switch between them in 2 minutes flat while on the telescope using an automatic filter changer system. Different filters are used to highlight certain objects or areas of interest. For example, infrared filters are useful to see through dust, as well as detect light from the most distant objects. And on the other end of the spectrum, the ultraviolet filter highlights hot young stars. All in all, this camera is awesome. I mean, it could fit 240 corgi puppies inside, and it takes 1,500 HD TVs to display a single image, not to mention the fact that it could find your lost golf ball in orbit. Now that we've recorded all the data, it has to be transferred and stored somewhere, and then made accessible to the scientific community. What's the point of making the greatest space movie of all time if no one ever gets to see it? The Rubin Observatory will be generating about 20 terabytes of data per night, requiring 400 petabytes of disk storage at the end of the 10-year survey for the 40 billion objects we expect to catalog. That's a B, as in bananas. 400 petabytes is an enormous amount of storage, equivalent to 400 million gigabytes, or over 1 million laptops worth of storage space. In fact, if you were to save all that information on a regular CD-ROM, my preferred convenient portable storage device, you'd actually need over 500 million CDs to save all the data, which would fill up an Olympic swimming pool 4 times over, and is particularly annoying because whenever you need one of the ones on the bottom, you have to suit up. Image data is handled in different facilities throughout the world, with a few different locations for long-term storage so that there's always a backup. The first leg of the journey is the fastest. After being acquired at the observatory, the data flows to the base center in La Sedena through fiber optic cables at a speed of 600 gigabits per second. That's like 120,000 people streaming Netflix in HD at the same time through the same connection. Efforts for me to tap into that bandwidth to watch HGTV remain, as of yet, unsuccessful. From the base center, the data flows south to Santiago, then through 2 redundant undersea cables up to Florida, and finally to the LSST data facility in Illinois for processing. LSST will generate 2 main types of data products during the survey: prompt alerts and full data releases. Alerts happen fast. As soon as each image arrives at the data facility a few seconds after being taken, it is immediately compared with a template, a previous image of the same patch of sky, to see if there are any substantial differences between the previous and current images. Major differences signal things like variable stars and moving objects. For each difference, an alert packet is generated and publicly distributed within 60 seconds of data collection, so that scientists can go back and study these areas of interest. We expect to generate about 10 million alerts per night, and I personally will be keeping my phone on silent for the next 10 years. The full data releases are the real end product, the space movie we're trying to make. The data facility in Illinois will produce and distribute completely analyzed images, which include calibration data, in addition to measurements of positions and brightness of objects. This official space movie will be made in parts. Each year, the entire available survey data set is reprocessed and then released to the scientific community, rivaling the quintessential summer blockbuster for most exciting film of the year. Sorry, Star Wars, second place again. Finally, when scientists are watching the movie, or at least tuning into some of these alerts, what are we actually looking for? The short answer is a little bit unsatisfying because it's everything. This facility is optimized for repeated full sky surveys in order to catalog as much as we possibly can of the southern hemisphere night sky. We will, of course, find lots of normal stars and galaxies and such, but also things we don't know about yet, and we need a ton of data to be able to find that proverbial needle in the cosmic haystack. After all, the words unprecedented discovery are written directly into the mission statement. For the Legacy Survey of Space and Time, Rubin Observatory has identified 4 main science drivers: dark matter and dark energy, cataloging our solar system, exploring the transient sky, and studying the Milky Way galaxy. Let's take these one at a time, beginning with dark matter and dark energy. It's not obvious why we'd use an optical telescope to study things we can't see. Dark matter is troublesome because it doesn't emit or reflect light like a nice, normal star. However, we can investigate how it influences the motion of stars and galaxies, as well as how it bends light from those objects, which will give insight into what's actually going on. The Rubin Observatory is named for Vera C. Rubin, a pioneering astronomer who discovered the discrepancy between the predicted rotational motions of galaxies based on physics versus how they actually behave when observed. In other words, she found that galaxies are moving in unexpected ways based on what we can see, which is strong evidence that there's something else out there that we can't see that must be affecting that motion. Namely, dark matter. The second science driver for this survey is a little closer to home, cataloging our very own solar system. Doing a thorough census of all of the objects in our solar system will provide insight into how it originally formed, and even how our own life-sustaining planet came to exist. That's only half the story, though. Cataloging all of these objects also allows us to efficiently detect near-Earth objects and predict if we're in danger of colliding with any of those asteroids. Although, to be honest, if I was a dinosaur, I probably wouldn't have wanted to know. The third area of interest is the transient sky, which we've already touched on when discussing the alert system. Because we'll be taking images of the same spot so often, we'll be able to see in almost real time the fallout of supernova and neutron star mergers and cosmic explosions, in addition to less explosion-y things like variable stars. The alert system tags anything that has changed, highlighting potentially interesting events and allowing the community to respond. For example, choosing to image that same spot a few nights in a row to catch these events before they fade forever. However, at 10 million alerts per night, it will be nigh impossible to follow up on every single one of those. Thus, the alert system will also be categorizing these differences automatically, flagging whether the change is a moving object, or flaring object, or burst, or maybe something new that doesn't fall into any of those categories. Perchance, an unprecedented discovery. The final science driver focuses on the Milky Way galaxy's structure and formation. The Milky Way is interesting primarily because it's not actually that interesting. Our sun is considered a fairly typical star, and the Milky Way is considered a fairly typical galaxy, and it's because of this extraordinariness that they can serve as examples for the general study of the growth and development of galaxies throughout the universe. It's hard to study a galaxy from the inside out, but that's why we're using a new, powerful survey telescope to do it. There are, of course, unlimited possibilities, and these areas of research are just a fraction of the space we'll be able to explore. To summarize, in order to do all that science, we have an extraordinarily fast telescope containing an extremely wide-field mirror system and a gigapixel camera delivering terabytes of data across continents to a petabyte data management facility that will provide real-time alert processing in less than a minute. With all that data, we're going to learn so much science every night. That's going to revolutionize astronomy.